Now we're going to look at nonlinear inequalities, and we're going to start in particular with quadratic inequalities. And our strategy here will be to take all of the non-zero terms to one side of the inequality and reduce our problem to deciding whether this quantity on the left is less than or equal to 0 or greater than or equal to 0, depending on what the inequality is. And then we're going to use this rule, and it's an obvious rule. If the product or quotient has an even number of negative factors, then its value is positive, because a negative cancels a negative. And if the product or quotient of a number of factors has an odd number of negative factors, then its value is negative. So multiply an odd number of negatives together and you get a negative. Multiply an even number of negatives together and you get a positive. So to use that, we actually factor the left-hand side, and then we have reduced our inequality to deciding whether the product of these factors is positive or negative. So it's enough to know the sign of these factors to figure out where they're positive and where they're negative. Okay, let's see how it works with this quadratic inequality. So as I said, our strategy is to bring across all of the non-zero terms to one side, and we have 0 on the other side. So we take over this 4x, and we get x squared minus 4x plus 3 less than or equal to 0 is our new equivalent inequality. Remember, the solutions to this are exactly the same as the solutions to this. Our next step is to factor the left-hand side of this inequality, and you can figure out two numbers whose product is 3 and whose sum is -4 have to be -3 and -1. And so this factors into x minus 3 times x minus 1. And now we've changed our problem to deciding when the product of these two factors is less than or equal to 0. And now we use our rule. These two factors are less if they're both positive, then the product is positive. If they're both negative, then the product is negative. And if one is positive and one is negative, then their product is less than 0. And of course they're equal to 0 when one of the factors actually equals 0. So we have to figure out where exactly one of these factors equals 0. And now, if we think about it, these factors can only change sign when they're equal to 0. So x minus 3, if I take the graph of y equals x minus 3, it switches from positive to negative where it cuts the x-axis. So exactly where x minus 3 equals 0. And similarly for the line y equals x minus 1, it switches from positive to negative. The y values, or x, the value of x minus 1, switches from positive to negative exactly where x minus 1 equals 0, or exactly where x equals 1. So we identify the points where these factors switch sign, and that's exactly where the factors equal 0. Once we've done that, we split our real line up into separate subintervals, and we know that on each of these subintervals, the sign of the product has to be the same. The sign of each factor remains the same on the entire subinterval, and therefore the sign of the product of the factors remains the same on each subinterval. So the first step is to identify the zeros of each of the factors, and as I said, x minus 3 equals 0 exactly when x equals 3, and x minus 1 equals 0 when x equals 1, and this gives us 2 points in the number line 1 and 3. Now this breaks our number line up into 3 subintervals. The first subinterval is from negative infinity to 1. The second subinterval is from 1 to 3, and the third subinterval is from 3 to infinity. And we know here that x minus 3 and x minus 1, their signs remain constant on this subinterval, so therefore the sign of their product remains constant on that subinterval, and the same holds for the other two subintervals. So our next task is to identify the sign of the product on each of these subintervals. So our next question is, what is the sign of x minus 3 times x minus 1 on each subinterval? And we know it cannot change sign on any of the subintervals because neither of the factors can change sign. How do we do this? Well, we have two methods. Our first method is to identify the sign of each of the factors on each subinterval and then multiply the signs to figure out the sign of the product. So we list the intervals. We have minus infinity to 1, 1 to 3, 3 to infinity. We look at the sign of each of the factors. Sign of x minus 1, that's negative if x is less than 1, and it's positive if x is bigger than 1. So it's negative on this subinterval and positive on the other two. And the sign of x minus 3, the other factor, is negative for x less than 3. So it's negative on these two subintervals and positive on the interval from 3 to infinity. And then the sign of the product is essentially the product of the signs. So we have the sign of x minus 1 times x minus 3 on the interval from minus infinity to 1 is a minus by a minus, so it's a plus. And on the interval from 1 to 3, it's a plus by a minus, so it's a minus. And the sign of the product on the interval from 3 to infinity is a plus times a plus, which is a plus. So now we have all the information we need. Our problem was initially to find the solutions to this inequality. The inequality x minus 1 times x minus 3 is less than or equal to 0. So we wanted to identify all x where this is true. And we see from our picture here that this is true for all x values between 1 and 3. In fact, for all x values between 1 and 3, we have the product is less than 0. And we have the product equals 0 at the points where one of the factors equals 0, so that's at the endpoints 1 and 3. Therefore, the solution set to this inequality is the closed interval from 1 to 3, because we're looking at less than or equal to 0. The other method of figuring out where this product is positive and where it's negative on the subintervals that we have identified is to pick any point in each subinterval and test its value, because we know that the sign of this product cannot change on any of these subintervals we've identified. And so if we pick any old point in each of the intervals and check the value of the function, that tells us whether the thing is positive or negative. So for example, if I pick the point x equals minus 2 as a test point in the subinterval from minus infinity to 1, plug in the value into the product instead of x, I get minus 2 minus 1 times minus 2 minus 3 gives me 15, which is positive. So the product is positive at the test point, so therefore it's positive on the entire subinterval. On the interval from 1 to 3, I pick the test point x equals 2. I pop it in instead of x in the product, and I get the value -1. And so the value of the product is negative at the test point, and therefore it's negative on the entire subinterval. And for the interval from 3 to infinity, I pick the test point x equals 4. I plug it into the product. I get 3, which is a positive number. The value of the product is positive at the test point. It cannot change on this interval, so therefore it must be positive on the entire interval. And again, I can draw the same conclusion here. I have that this product is negative between 1 and 3. It's equal to 0 at the endpoints. And so therefore the set of all x where this is true, x minus 1 times x minus 3 is less than or equal to 0, is the closed interval from 1 to 3. Try these techniques with this inequality. See if you can figure out where the inequality is true, the values of x where it's true, and then watch the next video to get the solution.